So let's tackle this problem where I have an equation to solve. My variable v happens to appear on both sides of the equation in this example, and the coefficients in my equation happen to include some fractions. So what's a good strategy to use? What's the first thing that might jump to mind as a good idea to help solve this problem? Okay, great. So one of the things that we know we're going to have to do at some point is we're going to have to combine like terms, particularly because we have two different terms that have that variable v inside them, right? So if I want to get the v by itself, the first thing I need to do is get the v's together, right? Maybe the first thing, maybe not the first thing. We'll see. Depends on how we choose our strategy. But at some point, we're going to have to cross that bridge. We're going to have to combine like terms. What else? What other possible elements of strategy could we use here to make solving this equation a little bit nicer? Okay, so an option would be to find a common denominator and then do what with that common denominator? So first of all, let's look at these fractions and decide what common denominator could I use that unifies all three of these different fractions together. Yeah. Remember, how do we come up with a common denominator for a set of fractions? What are we looking for? We're really just looking for a multiple that is common to all of the denominators in the puzzle, right? Well, two of these fractions have the same denominator. Two of these fractions have the denominator of 4. So we don't really have three different denominators to worry about. We really just have two, because whatever denominator we can find that's common for both of these fractions will also be common to the third one. So it's really just the 3 and the 4 that we have to worry about. So what we need is a multiple of 3, which is also a multiple of 4. And the smallest number, which is both a multiple of 3 and 4, happens to be 3 times 4. Right? And remember from last time we talked about this, just multiplying the denominators together will always work. Right? If I just want to multiply them together and get 12, that's fine. We can do that. In this example, it also happens to be, so 12 also happens to be the least common multiple in this example. So let's make that sort of our first observation here, that the common denominator for all these fractions is 12. A common denominator, I should say, for all these fractions is 12. Okay. So now that we know that, how do we use that? See, if you remember back to last time we talked about two different possible approaches to solving this problem, solving an equation that has fractions on both sides. Option 1, option 2. I'm going to recopy the equation down here in my option 2 box. Minus 4v plus 7 over 4 equals minus 3/4 v minus 2/3. Option 1 is just to solve this equation like normally, right? Normal strategy. And the normal strategy for solving an equation is to simplify both sides, to gather the variable to one side, and then unwrap the variable by reversing the order of operations. So I'm just going to write here SADMEP. Right? Do all your subtraction and addition until there's none left. Do all your division and multiplication until there's none left. Worry about exponents and work parentheses from the outside to the inside. So that would be option 1. So for that option, and I'm not going to do all the arithmetic here, but for that option, the first thing we'd want to do is simplify both sides. Well, both sides are already simplified completely, because there's no like terms between these two, and there's no like terms between those two, so the simplify is done. So to gather my variable to one side, what I would have to do is add or subtract the variable terms. So, for example, I would add 3/4 v to the left and the right side. I'm going to skip a detailed discussion of the arithmetic here in the interest of space. And then over on the right-hand side, I have negative 2/3. Now that my variable is only on one side, I can unwrap it by reversing the order of operations. That's going to require me to first finish all the addition and subtraction. That calls for me to subtract 7/4 from both sides. And then continuing to the top of the next column, I would have negative 13/4 v equals negative 2/3 minus 7/4. That's going to be negative 29 over 12, I believe. And then to finish, to get the v by itself, I would just have to divide both sides by negative 13/4. Divide by negative 13/4. And then v would be all alone, which is great. It's exactly what we want. And then we would have negative 29/12 divided by negative 13/4. And that's going to give me negative 29. Nope, it's going to give me 29 over 39. So I skipped a complete discussion of the arithmetic. I'm just going to kind of cruise through that. Okay. But again, this would be the straight-ahead strategy, brute force, head-on, solve it exactly the same way that we would solve it if there were whole numbers instead of fractions. Right? The cost of this strategy is that we had to do a lot of fraction arithmetic along the way. And anytime we have to do a lot of fraction arithmetic, we're setting ourselves up for a lot of potential errors. Fraction arithmetic is fraught with potential problems. Because look what I had to do. I had to do negative 4 plus 3/4 to get negative 13/4. Then I had to do negative 2/3 minus 7/4, so that required a common denominator. Well, so did this one, I suppose. That gave me negative 29/12. And then I had to do a fraction division. Divide negative 29/12 by negative 13/4. And there's another chance for me to screw something up, right? Fact is that very few beginners in algebra have the presence of mind to navigate that many consecutive steps of fraction arithmetic without making at least one error. So this way, to me, is going way over the top of the mountain to get to the other side. What I would rather do is find a way to go the path that leads around the side of the mountain so we don't have to climb as much, right? And we might not twist our ankle if we go the other way. So what's the other way? If that's option 1, what is option 2? The technique that saves your bacon is called clearing denominators. Totally underrated. I don't know why every algebra student doesn't learn how to do this instead of that. Right? Because here there are 3 steps to become ruined. Here there's maybe at most 1 step in which we have to contend with fractions. But after that 1 step, if we can get through that 1 step without making an error, then our equation will have only whole number coefficients in it. And as soon as it has only whole number coefficients in it, your odds of solving it the rest of the way correctly go up about 4-fold. Because once the fractions are gone, life gets better. Let's face it. I'm a mathematician. I don't like fractions any more than you do. I like lower cognitive load problems to problems with a higher cognitive load. That means I really, just like you, I prefer to think less in solving a math problem compared to having to think more, right? If it's at all possible. And it is possible if we take option 2 and choose first to clear denominators. So what it looks like is it just adds a step before what was previously our first step. Clear denominators. So this is option 2. Whoops. So what clearing denominators means is it means taking this 12 and doing something different with it. So we identified, first of all, out of the chute, that 12 is going to be our common denominator that's going to be useful in this problem. It showed up when we took option 1 right here, actually. Right? So when we did this subtraction, we ended up with a fraction expressed in 12ths. So here we're going to use that 12 in a different way. When we clear denominators, what we're doing, so I'm going to put that little explanation down here, is we're multiplying both sides of our equation by a number which is large enough to cancel out every factor which resides in a denominator in the original equation. And that number is is any common multiple of all the denominators. If we use the least common multiple, we get the least amount of work. Okay? So here, clearing denominators means multiplying both sides of this equation by 12. And the idea, again, is that once I've done that, all my fractions will be gone. I'll have only whole numbers to work with, and then life is good. Crack open a beer, finish. So let's do it. What I want is to multiply, again, both sides of this equation, multiply it by 12. And so the upfront work that we have to do is fraction multiplication. And remember, fraction multiplication is actually the simplest of all 4 arithmetic operations to do with fractions. So that's why using this technique also reduces our possibility to make errors in that way as well, right? Making errors in multiplication is a lot harder than making errors in addition or subtraction. So one of these multiplications is just a whole number multiplication, -4 times 12. So let's write that one out here first. One of the other prices that we pay here is that the whole numbers that we get tend to be somewhat larger than the original whole numbers that were in the problem, but that's a small price to pay for getting rid of our fractions. So the next one of these is 7/4 times 12. So let's talk about a couple different ways to carry that out. One way to carry that out is just to approach it in the way that we usually multiply fractions. How do you usually multiply fractions, by the way? Straight across. So then we would have to multiply here 7 times 12. That would give me 84. And then 4 times 1, that would give me 4. And then I would have to reduce 84 divided by 4. So I'd have a division problem to do. 84 divided by 4, 21. Right. But let me pause, now that we know that that answer is 21, and ask, would there have been a quicker way to know that 7/4 times 12 is 21? How does 21 relate to the numerator and the denominator of the fraction 7/4? Is there another way we could have gotten to 21 other than the way we just did?
Reduced, right?
Yes, reduced what?
Reduce the denominator on the 7/4 and the numerator.
Yeah, right.
12/1.
Yeah, here's the great thing about multiplication. Multiplication is commutative. That means it doesn't matter which order that I multiply two numbers, right? I end up with the same answer either way. So what that lets me do, because I know when I multiply fractions, I'm just going to multiply across anyway. It won't matter if I multiply the 4 and the 1 in the denominators in that order, or, and this is the cool part, if I transpose them. So I'm going to take this 4, and I'm going to move it over to here, and the 1 and move it over to there. That didn't show up particularly well. Let me rewrite that. So I'm going to take the 4 that used to be over here and move it over here instead. And the 1 that used to be right there, I'm going to put over here instead. So that what I end up with is something that looks like that. 7/1 times 12/4. Well, what's great about that? 7/1 is just 7. And 12/4 is just 3. And 7 times 3 gives us our 21. So those are the subtle steps that go into the cancellation that Greg was talking about, right? And to me, when I do these problems, in my head, that's the mental gymnastics that I tend to do. It tends to be an easier way to go, because it doesn't involve us scaling the 7 way up to 84, only to cut it back down to 21. We instead scale the 12 down to 12/4, which is 3, and then multiply that by 7. Whichever way you choose to go about it, that product ends up being 21. But getting some practice doing it both different ways, I think, is beneficial. If we take that same tack for our next pair, -3/4 times 12, what do you think is going to happen? So let's say I have here -3/4 times 12/1. Well, now what if I flip-flop these two denominators? What does it look like then? What's -3/1?
-3
Negative 3. And what's 12 over 4?
3/1.
Right. And 3 over 1 is just 3. So what I have is negative 3 times 3, which is another name for negative 9. So when Greg was talking about cancellation before, or reduction, what he was really saying is that this 12 and this 4 can be reduced down into a 3 and a 1 just by dividing by 4 in the numerator and denominator. That's another way that people sometimes keep track of this calculation. I prefer to do it the other way, but your mileage may vary. Either way, we end up here with a negative 9. And then finally, negative 2/3 times 12. This 12 divided by this 3 is going to give me a 4. Multiply that by 2. It's going to give me minus 8. So we front load all of our fraction arithmetic when we clear denominators. And the only fraction arithmetic we have to do in this method is multiplication, the easiest thing that we can do with fractions. Right? And now all of my fractions are gone, and I can get back to my ordinary strategy for how to solve an equation, doing so now only with whole number arithmetic. Let's carry it out and make sure that we still get the same answer that we had before. So the first thing I would want to do is simplify both sides. Well, these are already simplified because these aren't like terms. These aren't like terms. So that step we don't have to do anything about. So the first thing we really need to do something about is to gather the variable to both sides. What should I do here to make it so that all my v's are on the same side of the equation? Right. To get all the v's on one side, I should either subtract this term by adding 9v, or subtract this term by adding 48v to both sides. I tend to like to have all my v's on the right side. That's just a weird preference of mine. You can feel free to disagree. But I'll just add 9v to both sides. And on the left-hand side, that gives me negative 39v plus 21. By the way, sometimes people will also bundle the next step in with this as well. So I know that I want only v's on the left-hand side, and I want only numbers on the right-hand side, and so sometimes people will at the same time also subtract 21. It's probably a better practice to do this in 2 steps, but just in case you find this to be a little bit more efficient, I can do it in 1 step instead. So I added 9v to both sides to get all my v's to the left. I subtracted 21 from both sides to get all my constants to the right. And now I only have 1 step left to get the v by itself, which is to do what? Divide by, by negative 39, the coefficient of v. And we find that when the v is by itself, its value is negative 29 divided by negative 39. What happens when you divide a negative by a negative?
Positive.
It becomes positive, right? So a fraction with a negative in both numerator and denominator can be simplified by getting rid of the negatives. And sure enough, we do end up with the same answer, okay, which is a good thing, because if we didn't, we'd be in super trouble, because at least one of our methods must have been wrong in such a case. But yeah, so I like this method better personally. I recommend it to every student in algebra because if your fraction arithmetic is shaky, this is the way that's going to help you to avoid errors more than the first way.